leaving it. I'll see if I can, how far I can go. I have 10 minutes, right? To the formula, the integral formula that we try to do the inverse Laplace transform. Instead, look up the right. So what we are doing is so you have this fs, right? The Laplace is the Laplace transform of capital F. So infinity is d f dt, right? And we try to get the inverse transform, right? And so the inverse transform will be related to, coming from the transform, obviously. This is the Laplace transform f, little f is Laplace transform f. We want the inverse transform that using this Laplace transform that doing something like the integral, then we will get a result. That would be our goal. So we can use something to, so this formula we write as inverse transform, inverse Laplace transform of this F. That's right. And so the first thing we compare, because in Fourier transform we have the inverse transform formula, which is symmetric to the transform formula. So we have that, but in Laplace transform we don't apparently have that, and there are some differences. The first difference is the limit, right? This is 0 to infinity, Laplace Fourier transform minus infinity to infinity. So the first thing you can do is just extend the limit. Say if we just, instead of integrating f, we can integrating f multiplied by a step function. So then we can extend the limit. So this f t multiplied by the step function that we talked about already. Right. That is the get rid of the first difference between Laplace transform and Fourier transform. And in that case, we want to get the transform, inverse transform for this function. So f times theta is now the inverse transform as f. Right. Now the second problem is this exponential function. And in Fourier transform, this is either e to the I omega t or minus I omega t. Right? But this is an exponential function. And the physical, I mean, with this exponential function, this f, capital F, may not produce a Fourier transform, because this only exists if you multiply by exponential function with large enough s, right? That would kill all the large dependency. I mean, the f at large t, because the exponential function, even f is maybe not well behaved or doesn't decrease, goes to zero fast enough. You multiply by exponential function and make it go to zero fast enough, the integram, you can still define your integral and get the Laplace transform out. So, so that if you just do an inverse Fourier transform of this capital Ft, that might have problem. So instead, we multiply this function, say multiply this function with a exponential decaying function. So we define g like that. Multiply by a decreasing function, the minus beta, for a positive enough, large enough beta times t, and then ft. Right. And then you can keep the theta function here. It doesn't matter. Let's see what your text is defined. Right. Right? Either you multiply this by it doesn't matter that much finally, right? Now once we do that, multiply by a large enough with a large enough beta, this exponential function will make the integram well behaved, and so that you can get the Fourier transform of this G. So let's see over here. Maybe now we change the convention, not using the symmetric convention, using the convention with no 2 pi factor when you do the transform, and then you have 1 over 2 pi at the inverse transform. This is to be consistent with the Laplace transform, right? So we define this as SGT, then integrate with the exponential factor, right? GT, and we are using this convention, minus I omega t in this transform formula. Okay, and now that is fine. So once we have that, we can now solve for this G, capital G, by the inverse transform of little f, right? So then we can write ft as basically you multiply e to the beta t, and the gt, which is given by the inverse transform of that, you have 1 over 2 pi integrate g omega, and we needed I omega t, right? And then d omega. Okay, so so that is formally you can do that, but there's still some complications. First is this exponential function. So first you multiply this to the integram, 2 pi omega. You combine the two, you have beta plus omega. Right. And then d omega, and we can actually do a change of variable. Instead of d omega, we can say d beta plus I omega, and later we call it s. Right. And compare this with that, you have extra I here, so you divide it by I. Okay, so that this beta plus I omega is your new variable s. Okay, and so formally can write 2 pi I. Originally, it's t is minus infinity, but once we do a change of variable, st, yes. Now we need to figure out what the integration range. Now this is a complex number. S is a complex number, so this is an integration along on the complex plane along a path. Now we need to figure out what the path is. Now the S is on. So S. This omega, yeah, omega is S, yeah. And originally, omega is from minus infinity to infinity. S, so S is along beta at the lower limit of t, at lower limit of omega, lower limit of omega minus infinity, so it's beta minus I plus I minus I infinity because of this omega plus I omega, so minus infinity beta plus I. Okay, so this is a path. If you look at the complex plane of S and given beta, beta is right multiplied by beta. Most likely beta is positive, but we'll figure out what the condition of this beta value, right? And then it's going from minus infinity in the imaginary part to the positive infinity, so along this line. So this is our integration path in here. Okay, and now we still need to figure out what the relationship between G and F. Right now, this is integrating over this formula involves this little g, but not F. Right, so we need to figure that out, and to figure it out, so let's find a space to do that. Let's do it here. Hopefully, I have some space. Now, you want to get but almost time. So actually, over time. Let's see if I have enough of time. It's still a minute here. So, and just like this G at or you can start from this F S is beta plus I omega. So going back to here, I can just erase this one and evaluate that S is beta plus I omega. Okay, this becomes a beta plus omega times P, right? And then we have already extended the theta function over here. So this is minus infinity, right? That, right. And now we can go back to that Fourier transform, right? Because we define this G as minus beta t times f t times theta t. This is exactly this one. This is e to the minus I omega t. And this is exactly this one. It's exactly this one. So G omega is f beta plus I omega, which is f, right? So we can change it back to. Okay, so that is the formula. So this equals to f. This integral is the formula. And we're not done yet, but I'm out of time, so we need to figure out what the beta value. So we'll talk about that later. The next time, just this time we get to this formula. There's a name for this integral. This is called Bromwich integral. Okay. But next time we'll start with here and discuss how you choose the beta and how you solve this in a kind of a genetic way, finding a formulation how you calculate this integral. Right? Okay. Because we already derived that this formula, what we call the what they call it, Bromwich formula. Bromwich integral. Bromwich integral. Okay. Whatever that is, we derive that, but one last step is to determine what the beta value is. So the formula is like that. So you have the formula Laplace transform of using the ft capital F is your Laplace transform with the S. And the inverse transform, we divide that. Once we're given this Laplace transform, we want to calculate ft. But the formula actually explicitly requires that the integral is 0 for negative t. So you can make sure that by multiplying that function, yeah. the formula is 1/2 pi I, and that beta minus I infinity plus I infinity f s and e to the st and ds. Okay, so that's the formula. That's the integral, Bromwich integral. So that is a compact integral on the compact S plane. Right. So 0. So what we need to choose is choose a beta, some large enough beta such that it satisfies this requirement that for negative t, it will give you 0. Okay, so that's the requirement to determine beta. And the idea is that you can now apply the Jordan lemma, except that now it's just the 90 degree. Usually Jordan lemma, we integrate along the view axis and close it either up and down. But now this is integrate along the vertical line. So you can either close it left or right. But it's the same because now the Jordan lemma, usually you have an I here, but you don't have an I here. Right, so this is already an exponential function. So what you require is that the exponential function, the argument is negative, but you close it on the semi-infinite circle, so that along this semicircle, the integral will be 0. Okay, and so that's the requirement. So now for negative t, so that t is negative, you require the real part of S is positive. You want to close it along a loop that the real part of S is negative. Okay, and so it means that you close it on the right. So was negative t. You want to close it on the right hand side, and so the integral along the semicircle is 0. So this is your Bromwich integral. So this plus that should be the whatever the contribution inside the singularity inside, but you require to be 0. So you require this line to be 0, but this curve is also 0. It means that inside you should not have a singularity. If inside the other way around, if inside is analytic, if this is inside, then you automatically the whole loop is 0, the curved path is 0, so the straight line is also 0. So that will make sure that it satisfies this relation. So the integral is 0 for negative t. It's okay. And the way to make sure that it's analytic is that all the singularity of this integral, so including the exponential function, but the exponential function is analytic anyway. So just the singularity of this Laplace transform. So whatever they have at Laplace transform, sometimes it can actually, in some cases, has a branch point and branch cut. So it could have a branch point and branch cut. So, but if it doesn't have branch point, so we only have singularity, that will be a little easier. But anyway, whatever singularity, including branch point or poles, you want to choose a beta to the right of all these non-analytic locations. It's okay, just choose a large enough beta, and then to the right of this line will be all analytic. Then you can close the loop on the right and make sure that the integral is 0 for negative t. It's okay. So that's the condition to choose beta. All right. So that would be choose an appropriate beta that was set 0 for negative t. Right. And now the other way around for positive t, then obviously now you close it the other way around, because again the Jordan lemma t is now positive. You want to close it with negative real part of S. So you close it the other way around. This is 0. Assuming that this infinite curve can enclose all the singularity, And assuming there's no branch point, and so you don't need to cut the branch cut, then the result would be 2 pi I times the residue, sum of the residue, because this is the correct size. This is a positive loop integral. This loop integral is equal to 2 pi I times the sum of the residue. We already have a 2 pi I in the denominator, so we just the rest is just sum of the residue. The residue is, remember, is this one, including the exponential function. Don't forget this exponential function, not just the Laplace transform. Is that okay? The residue of the whole thing, so F-E-S-T. Okay. And that is the usual case. And if there's a branch cut, then it becomes more complicated. So you cannot actually close it. And so in that case, you need to do something a little strange. So you can still deform it. Say if there's a branch cut, then you obviously cannot close it across the branch cut. What you need to do is just kind of move the straight line and deform it as you go. But then you cannot pass anything there. That path becomes like, well, we can still go like that, but you don't want it. You don't want to cross any singularity. It becomes something like that. Right. And you start with beta. Right. Deform it to enclose all the singularity. Right. Then all this at infinity, that will still be zero. But then all this path will cancel this straight line. So basically this is like a residue. It's like you count all the residue, but the branch point along branch cut, you need to be a little careful. You need to, because this two doesn't cancel along this and that doesn't cancel. You need to calculate that. And then the rest are all the rest of, I forgot this. Is that okay? So if a branch cut, that make life difficult. If without branch point, it's just some residue. Is it okay?
So in this case, where will the beta?
Yeah, it's still start with a beta, whatever the beta to the right. So you choose to say this is your largest S real part. So you choose a beta that is positive. That would be fine, but then and the exact beta value doesn't get into the integral anyway. So you just start with still a straight line, but still deform it, and then get back to here, right? But the end result doesn't actually depend. Okay, right? If that is so, the rest is just doing some example to illustrate that the process, which is very elementary. So I'll just go through that. Okay, so we got all of these, right? So now this first example is whatever that is. 20.10.1, the F is A divided by S squared minus A squared. This is A divided by S squared minus A squared. And this one is simple enough. You look up the table, you know the answer, right? But we use the integral to recover that, right? And now you just put this into here, right? So, or if you know the formula, you just directly substitute this into here, calculate the residue without going through the argument. But if you go through the argument, then you look at the pole. So this is S plus A times S minus A, so there are two poles. One is at A, the other is minus A, right? And the first thing you do is choose a beta to the right of all these. Oh, there's a beta, right? And the argument is that for negative t equals on the right, and that is means that the integral is 0 to the left, and for positive t closer to the left, and that will give you singularity at A and minus A of this, the residue of this whole argument. Okay, so there's so for t positive, you can just write Fb equals to sum of residue. So you have an A overall constant A. And then there are two poles. One is S plus T, S minus T. That pole A multiplied by S minus T only has S plus T in the denominator. You evaluate S equals to A. You get your 2A in the denominator. And there's an exponential function, so e to the A, e to 2A. Okay. The other residue is at minus A, you multiply S plus A. So you only have S minus A in the denominator, and S is you evaluate minus A, so you minus 2A in the denominator. Minus 2A. And the exponential function becomes e to the minus A. Right? And you cancel A, and the rest is just a sinh function. A sinh function. This is the definition of sinh. Right? That's to be the answer. Yeah, that's the F. That's the F. I multiply by the theta, the step function will be the integral for all t. This is for positive t. Let's see. Okay, so that's the first example. Is that okay? It's somewhat trivial enough. The next one, the second one. I just erase it instead of going the other way. Is that okay? I can erase it. Yeah. The second one is F S 1 over S 1 minus e to the minus A times S. Right. And that one is more complicated because of this exponential factor, and so that you need to be a little careful because how you close it, on the level on the right depends on the value. Right? This is the only singularity is S equals 0. That's the only pole. And now it depends on t now. Right. The first thing is still for negative t, you can close everything. So let's just write this, substitute this in the here. So let's just write the F times this because that's the integram. The integram is 1 over S. You separate into two terms. One is just the original exponential function S times t. The other is a little more complicated. It's S times e minus A. Let's see. Okay, so this is the integram. Now for negative t, this term obviously you can close it on the right. And for negative t, both are negative, so it's still negative, right? So you can still close it on with real S, a real positive S, right? So you can still close this one. Choose a beta to the right of pole, which is any positive value of S. Okay, this value is beta. Okay, and now to the other case. There are two cases. One is what S is really for S is large, or S is really large, both are positive. Yeah, T, so all you can the integral that's right. You have to figure out that there is 0 for negative T. And then the next case, T greater than A. Right. T greater than A, both are positive. So this is, you can close it the other way. This is T negative. T is greater than A. You can close the loop on to the left. And both of the exponential function will contribute to 0 along this path. So the path doesn't matter. So you only calculate the residue at x equals 0. So the integral will be sum over residue. Actually, there's only one. So the residue is at this pole. So you multiply by s and evaluate everything at s equals 0. For s equals 0, both terms are 1. So this is 1, this is 1. So you subtract the 2, it becomes 0. Right. Right. The more complicated situation is for the other part. S is between 0 and A. Right. In that case, this is positive. The argument, this is positive, T is positive, but this argument, the exponential function, this is still negative. T minus A is negative. So for the first term, so now this is for T between A and 0. Then there's two terms. So each term you close it different. The first term you close it to the left. First term. The second term is still negative. This is still negative. Then you close to the right. Second term. Right. Yeah, this is the axis. I actually close it this way. Yeah. For the second term, for the first term, close it this way. The second term, close it this way. Okay. It's a little bit confusing, the graph. Okay, yeah. So now the second term is easy. The second term, when you close it to the right, then there's no singularity. So the second term will be 0. The only term that contributes to the integral is the first term. Then you evaluate at the pole, which is s equals to 0. And so cancel the denominator, and e to the 0 is 1. It's 1. It's okay. So that the final result is this function, this ft beta t function. It's just a head function. It's the head function. So what's negative t, so around t, negative t is 0. And then between 0 and a, there's an a. Between 0 and a, jump to 1. And then go back to 0 to this one, this one, this one. Okay, so that is the result. And you can write it down using a difference in step function anyway. So it's okay. So sometimes it becomes a little more complicated. It's not always that you close it for positive t or only one, because that can be complication. In that case, you need to be a little careful. Go back to your complex analysis, complex integral method, determine how to do it. Is that okay? That should be all for this section.